Next up on our list are the methane digesters. There are large and small ones. Both are ranked here. By 2050, the large ones rank at 30 with 8.4 gigatons of reduced CO2, $201.4 billion in net cost, and $148.8 billion in net savings. Whereas the small methane digesters save about 1.9 gigaton in reduced CO2, $15.5 billion in net cost, and $13.9 billion in net savings. I think pretty much everybody has heard of methane digesters. Way back in the 1970s or 1770s, it was already recognized that anaerobic digestion of organic matter was producing methane, and it was highly combustible, so could serve as a energy source. This is just a map of worldwide benefits realized by methane mitigation projects. So Global Methane Initiative partner countries shown in dark green here, and locations of case study projects with these gold stars. They are not placed to represent exact location of the project within the country, but just placed on the country. The four highlighted projects in this report alone will eliminate more than 150,000 tons of CO2 per year. So this is a globalmethane.org website. So you have Canada, US, Mexico, Peru, and those are the highlighted projects, India and South Africa. But you can see that many countries are involved in the use of methane mitigation for projects, and also to generate energy or heat from them. Overall, the anaerobic digestion process, I hope everybody listening to this knows what anaerobic digestion basically means. It's oxygen-free air that drives anaerobic consumption of the organic matter that is fed in either agricultural waste, food waste, or biosolids and organic wastewater. And there is a pre-processing involved before feeding it to the anaerobic digester with post-processing of solid and liquid effluents. Solids can produce compost and animal bedding, and liquid products can be used as organic fertilizers. So there is a potentially useful byproducts there as well. But every time you have such byproducts, one has to worry about potential leakage, contamination of groundwater, soils, etc. And of course, methane is 25 times more powerful in terms of its greenhouse warming potential over a duration of something like 100 years. It has a lifetime of residence time in the atmosphere of only a decade, but it converts to carbon monoxide, which then converts to carbon dioxide, so it's not a very friendly gas either way. From the anaerobic digester you can get biogas, where impurities have to be removed, and then either electricity can be generated by using that biogas as a fuel for driving engines, turbines, etc., or they can be used directly to burn off methane to produce thermal energy. Of course, they can also be used as fuel, so pipelines and vehicle fuels and so on. There are lots of reports on unintended or intentional methane release by producers of natural gas or byproducts of oil production and so on and so forth. Methane leak is a big problem, and it's much larger than we had heard of. So from those four projects that are highlighted in this report, there are listed recognized financial, environmental, and social benefits. So this local production reduces transport and disposal costs by also using the byproducts, as we mentioned. Reduces energy costs for equipment, lighting, and heating. Reduces costs from organic fertilizer use because the byproduct produces fertilizer. Increases income from scale of energy. This is again the energy poverty issue, energy security issue, and depends on exactly how it is done, because there are people who will argue that this is not all it is cracked up to be. Increases income from sale of fertilizers, increases revenue from larger crop production by using fertilizer byproduct. So this is from one of the projects. Recognized environmental benefits, I think this is from Brazil, where reduced greenhouse gas emissions and improved air quality is seen. Improvements in water quality by lowering eutrophication effects, where releasing directly the organic waste into the water bodies can create excess nutrients and phytoplankton blooms, some of which can be harmful sometimes on their own, but when there is a bloom and it's not grazed down by zooplankton, which don't grow as fast to a nutrient burst and phytoplankton bloom, the phytoplankton die and sink, are then digested by aerobic bacteria, which consume all the oxygen, which is what we call eutrophication. So wastewater release into coastal water and so on are, for example, plus livestock or poultry farm waste release into groundwater and so on, have caused a lot of problems in various places. Decreases odor, lessens pest issues, replaces chemical fertilizer with organic fertilizer, decreases use of firewood, helping to combat deforestation. So just producing methane from methane digesters can reduce biomass burning for direct energy use, which instead is provided by these methane digesters. Social benefits include providing access to electricity and heating source, creating jobs, increasing skilled labor force, and improving sanitation and public health. So this is obviously context dependent on where this is being done. In a developing world, that's true, but not necessarily for rich countries. Germany, I think, is probably the largest micro wind, and maybe methane digesters are everywhere, more evenly distributed than like solar, wind, micro wind, and concentrated solar power, for example, etc. Our analysis includes both small and large methane digesters here, as we saw in the beginning. We project that by 2050, small digesters can replace 57.5 million inefficient cook stoves. This is a big deal for a country like India, countries in Africa, South America, and so on, in low-income economies, while large digesters can grow to 69.8 gigawatts of installed capacity. The cumulative result would be a 10.3 gigaton of carbon dioxide emissions avoided at a cost of 186 billion over the lifetime of, or over the 30-year period we're considering out to 2050. Okay, we'll leave this here and then move on to the next energy sector.